It's a great pleasure to be able to speak today in front of younger people, as well as some of my very old but still young friends. And before I start, I would like to say that this is the first in this series of talks that myself and Professor Garban will be giving in the next couple of weeks. Somehow, remarkably, they will be, we'll keep the balance of, let's say, good and bad things. And when deciding who is going to talk about what, we have agreed that I will be the devil advocate, the one who is talking that everything is bad, everything is hopeless. Yes? Okay, thank you. This is apparently naturally AI is still needed, right? So that we can move about. So yes, I'm going to talk about everything which is bad, etc., and Professor Garban is going to talk about how everything is good. So and in the end of the day, you decide for yourself what is good and what is bad. So this is somehow again funny because today's talk, even though it's the first in this series, chronologically, when it comes to results, it's the last one. So it's more or less like the fresh result, pretty fresh result, which we have received 1 year ago, but the journey was very long. And I think without any further ado, I would like to start with the presentation. So the talk is about accuracy stability paradox, and what I hope I'll convince you all, if you believe that AI is omnipotent and is capable of everything, I probably hope that I'll convince you that it's not, and there are some things which we need to be looking at very carefully, unless we want to assign some measure zero or probability zero to some eventualities. So, and that's the structure. So again, because it's the first talk of the series, I would like to talk about AI errors and issues, and somehow about the way they unfold in real life systems. And then I want to formulate what we call an accuracy stability paradox, and probably from this title you already have a scent of what it's going to be about. And then I'll reflect upon this paradox and conclude the presentation from a sort of bigger picture point of view. So, and of course, it's good to start with a positive thing. Right? So, we have seen and heard a lot about the capability of AI models. And this is one of my favorite topics, in fact, to talk about. And here is what I took from a paper published about 3 years ago, actually nearly 4 years ago. And this is a paper about, the real good that AI systems can produce. And this is no joke, because on this figure, we see two plots. So one is the specificity sensitivity plot for an AI model capable of detecting a breast cancer. Right? So it's a very important job. And most importantly, what you see in this figure, you see this green dot, I think corresponds to a human reader, and the circle here corresponds to another human reader, and the rhomb here corresponds to the consensus reading of 2 medical professionals. So, and the curve here shows how the AI performs. And what we see from this curve, apparently, and very promising, in AI, a machine, when it looks that an image is able to perform on par on a UK patient to a medical professional, which is really amazing. So, and it's been a while, like there, like this capability is there. What is actually even more remarkable, if you look at the other plot here, so when the system was tested in the US, basically, this is a topical thing, like people are saying, look, it was trained on a different cohort of data, on a different sample, and yet performed well. So what happened is that this green circle corresponds to the reading of a single American doctor, and the curve corresponds to the machine. And you see how dramatically better the machine performs. So this picture alone probably would be enough. Like if I would be making a business pitch to some American clinic, probably I would win the money, right? Because people are expensive and the machines are very cheap. So to add more to the picture, here is another one, which is more recent example. And BBC was all over the place about that when people reported that apparently, like using very advanced, yet at the same time cheap, because it's a machine which does it, advanced system for segmentation of images in patients, doctors and clinicians could be able to identify and actually cut down the treatment, like, time for cancer radiotherapy. Like what it comes to, like it's a very typical thing. Like when you have a suspected patient, then the doctor typically looks at all the images and then they very carefully by hand do the annotation of those images to identify where the, suspected tissue, which is cancerous, is manually. And then it takes time, like several hours. It takes time per doctor. And thinking of like, if you have 1,000 patients to treat, that's, the scale. And the machine can do it very easy and fast. So that's what this whole thing was about. And in fact, that's what I took very recently. If you notice in May here, and here is the link to the source. Unfortunately, it's not very clear from the picture, but this is what is more or less expected from AI when it comes to the added value to the economy come 2035. And the expectations, especially in manufacturing, are huge, in professional services, in wholesale and retail, etc., and including in healthcare and in communication. Like you see, like there are some expectations here, and they are based and they're grounded on nice and actually very realistic promises and expectations. But here comes something else. And that's an example which I took from the paper, which is already about 7 years old, when people started to experiment, perhaps for the first time, with the autonomous driving. And this is a clear example of when and how things may go wrong. Because in this particular experiment, what these people revealed in their work is that, like, if you follow the stretch of the road, you have to kind of follow the path, and you shouldn't deviate to the right, of course, right? Like you have to drive your car so that it follows the path, right? At the same time, if you change the contrast of the image a little bit, this is what happened in actual simulations of that robot, right? So the question is, and that was unexpected, the question is like, how come? And why is this happening? So there are some other examples, of course, and this is, remember the slide which I showed about cutting time for radiotherapy, right? This is a very interesting slide because we've been working with my colleague, Jerry McCann, and he's a cardiologist. What they're interested in identifying and quantifying the sizes of infarct in patients. Right? So why is it important? Believe it or not, at the minute, when a person is like, and if or after a person suffered an acute infarct, or like, they are of course rushed into the hospital, they're helped there, but of course things don't stop there. And like after a while, they get back to the hospital, and then people start to like do lots of imaging on them and assess the damage, because that determines the prognosis, and that determines how medical practitioners should actually treat the people. Right? So the problem is, in many instances, at least that was at the time, you know, it's very difficult to manually quantify, you know, the infarct, because like think about like a heart, like you have 10 slices of this MRI scan in a heart, and then like the heart is beating all the time. You're looking at this video, like images of the sequences, and you should be able to manually contour the, you know, the scar tissue in the frames. Doctors do that. It takes about like 1 hour per patient, but they very rarely actually compute the volume. And we've been thinking with him, like, why don't we automate the process of, say, computing the volume of a scar? And actually, it hasn't been completed yet. So this task is still actual, because there are some complications, of course, interesting cases. But it's not about that. Like, and this is what the commercial software does. And he showed me, like, look, Ivan, isn't it nice? Because like I just had a new version of the software, and I ran a few scans to them, and this is what it showed me. And like, you see, like ideally this green contour should have shown the blood pool, like, or like the muscle boundary, but you can see it's not showing it because the muscle boundary is here. So this black thing, so like it's not showing the muscle boundary. And likewise, this red contour here should show blood pool, but it doesn't show the blood pool correctly. And what's important is this pinky part. So this is supposed to show the infarct, and it's not showing the infarct because the infarct is here, where the white arrows are pointing. So again, this is a commercial software, real scan, real life. So it's not happening. So the question, of course, why, right? And like this is very famous thing. Like when people started to look at, like, you know, these unusual performances, typical adversarial example, like actually they've been, even the paper explaining the harness in adversarial example, but in fact, before that, there was a paper about surprising behavior of neural networks, which are subjected to small, tiny perturbations, specific ones though. So, and we see that adding a little perturbation, which are imperceivable to us humans, we would still perceive this as a panda, I hope, but the machine perceives this as a gibbon, and likewise, the actual noise itself was perceived as a nematode. So the whole thing apparently is breaking apart. So it's like, you know, this perceived thing. And moreover, like if you want to probe in this direction even further, what's happening is that, let's say in this medical imaging, like you have a healthy organ, an eye, in fact, an eye, and you have a healthy lung and a healthy skin, right? It's just a mole here. But if you add some perturbations there, again, like imperceivably small, then all of a sudden that becomes a malign cancerous episode. This becomes a disease, and this becomes a disease too. So, and now think about that, like if you're a medical professional, are you going to trust these models? And that's a big question. And of course, an answer would be, probably I would if this is an exception, but can you prove that this is an exception, right? So, and you see, like I can carry on with these stories. Like there are many stories like that. I just want to set the scene, and as a proof, as a living proof that like there are many stories from time to time. IEEE Spectrum, which is one of the flagship engineering electronics journals, published an article about why AI cannot be trusted. And like, for example, how IBM Watson overpromised and under-delivered on AI. 2019, right? Here is another one, 2021, 7 revealing ways AI can fail. Think about that, right? And the more recent one, it's a very interesting one. Hallucinations. Hallucinations could blunt ChatGPT successes, even though like there are titles like that. If you ask me what a hallucination is, I will tell you I have no clue what that is. I don't think people themselves understand what they are. But despite that, there is still even a debate already going on. You see, like OpenAI says the problem is solvable, and Jan LeCun says it, we will see. So, and then there is something else, like I just wanted to add it, like there was a system in the US whose aim was to actually detect weapons, but it didn't, right? So, and as I said, like there is a whole plethora of examples, and I'm putting this on the slide here, just in case you wish to go and have a look. And the database is in fact growing about this, you know, AI fails, etc. Now, here's another one. Of course, people realize that things go wrong. But then there was a hope some time ago, like if you lived on this planet long enough, you would have noticed, like the last, like a couple of years ago, like maybe 3 years ago already, 3 to 2 years ago, people started to think, oh, but explainable AI is going to save us, right? Why don't we do explainable AI? Unfortunately, no, it's not going to save, because this is very interesting paper. Actually, the paper actually says that, well, explainable AI, if you design it from the same perspective of like pure black box modeling, is not going to help. Unfortunately, there is no way out, and they haven't proved much, but they made the case very, very strongly with the evidence showing how explainable AI suffers itself from instabilities and from all the other things, okay? Now, and I think I'm going to come to my first series of questions, which I'm going to discuss with you here. And the first question is, why do errors, and I would like to stress instabilities here, I will come back to this point of instabilities, in the state-of-the-art decision-making systems exist? Why are they so prominent? And by the prominence, I mean that they're detectable to us, right? Like if they would happen only 1 in a million times, in my time scale, like probably I wouldn't even notice, but why are we noticing them, right? So, and that brings me to the second point. Are these errors typical in some meaningful sense? The meaningful thing is important here, and I will come to this today in the lecture, because you can, and probably rightly so, you can argue that some of the examples which I showed are not meaningful. That's fine. We can discuss what does it mean in meaningful in this typicality, right? So, and finally, like not finally, is there a theory that enables us to understand what is wrong with those models? What is wrong with the approach, perhaps? And can we verify that an AI model is not brittle? So, and these are the questions I would like to throw at you. And I have to make a disclaimer. I don't know an answer to these questions, right? It's very easy to ask many questions, but some of them I will answer today. Right. And let's start. So like, I would like to start a little bit from I would like to step back and recall the the basic foundations on which statistical learning theory and the modern, let's say, data-driven AI rests as we know it, right? So the first one is the central limit theorem. We like central limit theorems because it enables us to simplify things, right? We like it very much. And close relative of the central limit theorem is the concentration inequalities. These are the, in a way, the basis of modern machine learning theory. So like we use them, these hovering bounds, Chernow bound, Talleyrand, like whatever, depending on the applications, we use them always to mathematically understand what's going on, right? So, and they, in fact, as I wrote here, underpin a large body of modern machine learning AI. And when I'm saying modern, I actually mean the results on which this modern system of knowledge is based, which are basically going and dating back to the 70s and 80s, right? That's modern. So, and here is another point. So like I started from this kind of like foundational questions, but you know, from time to time, every 100 years, maybe often these days, mathematicians like to gather together, and computer scientists too, and pose problems and challenges for the next century, right? Like that happened in the beginning of the 20th century, favorite Hilbert problems, which defined how mathematics in fact evolved. And that happened in 2000, also like at one of those congresses of mathematics. So Donoha in 2000 made a lecture on the mathematical challenges of the 21st century, right? So, and the lecture was the curses and lesson of dimensionality. And this is what like our team's schematic representation of where we stand at the minute. Probably that would enable us to understand things in a broader context. So like there is a classical area. This is where, according to like to the classical literature and also to the Noho, where the number of data points n is exponentially larger or comparable to the number of attributes that you have, right? So the attributes which determine, they describe your measurements, and the in the absence of knowledge about the distribution, etc., that's what we do when we work with these data-driven models. We always love the case where we have exponentially many data points, right? Like the more the merrier. But that's a classical limit where many of these classical tools work. And then he said that unfortunately, we are living in the post-classical area. In the post-classical area is where the number of data points actually is no longer much larger than the number of attributes. And in fact, we often have the case, for example, if you take a medical tasks, like a patient's record, right? In a typical, let's say, a hospital may have hundreds of attributes, right? So hundreds of attributes, you may say it's not very large because we have, you know, like maybe say millions of populations, but you will be wrong because if you take hundreds of attributes and raise 2 to the power of 100, then you see a huge number. And that huge number is nowhere close enough to millions of patients. You don't basically span the whole thing. You don't span the set, like that set is empty. And that's a problem. So, that's one thing. And then like, you might ask like, what may go wrong? Like it's still large enough. But the physicists know what may go wrong. And I'm going to give you an idea of what may go wrong. And it's very interesting because this is a famous margin capacitor law. Some of you may know that, and some of you not. And it is about the following. So suppose that we take a D by N random matrix with IAD entries. So like a very typical clean case, right? Like we have independently, identically distributed entries of the matrix, right? And we take a sample, like let's think of it as a sample. And then like the mean is 0, right? And the variance is equal to, let's say, sigma squared. And then we compute this term, like let's say we compute this naive empirical, let's say, covariance of this matrix. Why not? Let's do that. So, and then we ask ourselves, what happens with the spectrum? We actually want to compute the spectrum. Ideally, right, naive intuition would say that if n goes to infinity, then the spectrum would converge to the variance, right? Like this, the sigma to the diagonal matrix. So, and that's what we normally do, like why it's important for data science and for this AI business thing, because we do principal component analysis. Like when we have some high dimensional data, what do we want to do? Why don't we do SVD? Why don't we do PCA? We do that, and one of the criterions, remember that, to define the dimension, let's say, like a Kaiser rule, like you compute the eigenvalues, and then you take the average of them, right? And then you cut off everything that's, let's say, below average, right? That would be true and a good method if, of course, you would know exactly the eigenvalues. But the problem is, in some asymptotics and in some limit, where, for example, both the size of the data set and the attributes, the number of attributes go to infinity, but then you fix the ratio to, let's say, lambda, right? Then this empirical measure, which we constructed here, which is essentially the average of the cardinality of the set, like say lambda, one of the eigenvalues belonging to some interval or whatever we understand under this omega here, it converges to this object. And this object is interesting because it's no longer sharp and spiky. And in fact, it has a smearing. It has a smearing around sigma, and this is how it looks. So, in order for you to visualize that, I took it from Wiki, in fact, and then this density here is shown for different values of lambda. Remember, lambda is the ratio of the number of attributes to the number of data points, right? So, if you have different values of lambda, although constant, you see, you no longer have a peak, you have a spread out spectrum. So how can I use them, my favorite SVD or like principal component analysis, when I'm in this situation? Because that's, you see, like that's exactly the typical canonical approach that we are taught. Like if you have more attributes than the number of data points, do PCA, do SVD, but what does it mean? Of course it works, but probably it works for a different reason. Because it doesn't work for this reason. So you cannot estimate, right? Of course, under the assumptions of this theorem. Now, here is another one. Right, so, yeah. Here is another one. I want to keep amusing you with these funny things. So like, large data may not always be good because it depends what does it mean, large data, in which sense. Are we working in the post-classical limit? Are we working in the classical limit? It's important to understand that. So here is another example. And I think it's, the example is very interesting, and it's fundamentally based on like, there was a small paragraph in the classical Vapnik book, and then it was like taken over by other people. But look, what I'm going to have here, I'm going to look at a neural network and think of this sigma as some function, just like whatever, like sigmoidal function, right? So a W and BI and B naught, they are all, let's say, real numbers. Now, and I have a Heaviside function here. So like I'm thinking of a neural network comprised of the following like composition, Heaviside function of a sum of sigmoids, right? So, and then I ask myself a very naive and stupid question. Can I think of a arbitrarily small perturbation which I'm going to add to this system, and in fact I'm going to add it to every single sigmoid, the same? Is there an arbitrarily small in L infinity norm and also smooth? It's important to be smooth, right? Because we like things which are smooth, and we sort of trust if there is a smooth and small thing, then nothing is going to happen, right? What can go wrong? Right, which can radically change important properties. So like what I'm going to change here, you can think of like, what property can you change? And I'm going to go after the most important property, generalization capability. So like what I mean is that I'm going to say, can I add a little thing to the activation function? It was sigmoid, but then I want to add a little tiny bit. You tell me which tiny, I'm going to give you an example. But then, and I want to add it in such a way that I blow away your capability to guarantee any generalization in the model. How is that? Is it possible? The answer is, remarkably, it is quite possible. So I have to make again a disclaimer, though. In many arguments and proofs about generalization bounds from neural networks, what you have is you consider worst case scenario, right? Always, that's how the proofs goes. And the way the proofs go that way, because you refrain from any hint of knowing anything about the data distribution, right? So therefore you have to look at the worst case. What I'm going to say here is that unfortunately, that argument doesn't work anymore, because if you look at only those worst cases, you cannot prove anything. And here comes the result. This is taken from the book by Bartlett, 1999, but actually the whole machinery of the argument is already in the classical Vapnik's book, right? So what we say here is that I'm going to give you a 2-neuron function, a 2-neuron neural network. How much simpler it can become, right? So, and then I'm going to change my activation function in that way. Exponent, right, like a Gaussian, and then there is a sine function, and then there is a polynomial x to 3 and any arbitrarily small epsilon. And what happens after I add this term here to this function, like if you, again, like if you think about VC dimension, like Vapnik-Chervanenko's dimension, which is essentially the number of dichotomies the thing can potentially produce before that number starts to deviate from the exponential, right? So the VC dimension of this new network is infinite. Why is it important? It is important because if you were to write your favorite risk bound for generalization error, what normally happens is like you have like your actual risk is less or equal than the risk which you got on the training set plus the square root of a term which depends explicitly on the VC dimension in the nominator, and then is divided by the number of data points that you have. So if that thing which you have on the in the nominator is infinite, you cannot use that risk bound. Right? So that's another thing. And what I'm going to start now, and that basically brings me to essentially the core of my talk today. Can something similar be shown for small perturbations of data? So like in a slightly different form. Why I'm going to say slightly different form? Because on Wednesday, I will talk about the anatomy of adversarial attacks. This is where we are going to look deep into these adversarial attacks, why they work, why they don't work, and what makes them so unpleasant. So, but today I'm going to talk specifically about stability. And in order to set the scene and the notion, I would like to tell you what I would like to understand under stability. So like if you think of, say, classical setting, like you have a map which you want to use as a machine to decide something for yourself, right? You have a map, you have, and you want to use this machine to classify, let's say, you know, balls into white and black, right? So like, or make some other decision, like separate carrots from strawberries. Now, the machine takes a real element, like actually an element of a linear vector space, like Rn in this particular instance, and outputs something from the set of labels, right? So the set of labels is supposed to be finite, and therefore, when we have a definition like the first definition, the adversarial example, what we actually mean is that for a given classification map F, an element X admits the adversarial example Y of X if the label is different, right? And yet we remain within the delta distance from X. In this instance, let's use a classical L2 norm to make things precise. So that's what we mean by a delta adversarial example. So like the existence of something within the delta, with the given delta that swaps the label, right? And the nuance here is that when we are talking about instability, we are saying that it's unstable at X if for any arbitrarily small delta, there will exist some Y which swaps the label, right? So for any small versus there is a delta, right? So like this nuance will become important on Wednesday, because that's where I will be able to show what and why somehow adversarial examples are very bad, and they are probably not necessarily instabilities in the usual sense. So, and here comes the message which I want to communicate today. So the crisis of distribution agnostic learning. So I say it a crisis, like we discussed in a group, like how do we call it? And a crisis because simultaneously the following happens. And I will specify precisely what's going to happen. So a family of simultaneous paradoxical controversies exist. First, they exist perfect, accurate, and generalizing networks, not the ones which I showed you, the scary ones with a little addition in them. No, the good ones. Now, the problem is that they will, however, become unstable on some big set of, yet finite set of points from the training and validation data. Regardless of that, there will be accurate solution, which is robust. But the problem is we cannot tell if we've got a robust solution or wrong one or like unstable solution before we try and experience the instability, right? So it may sound controversial, but, and I would like to guide you through this setting. So in order for me to set the scene, and I apologize, the statement will be over 3 slides. But it's a funny statement, and I hope you will enjoy reading that statement. And I'll show you how you prove one after that. Very simple, one picture. I like proofs by picture. We had a meeting with Alexander Vladimirovich just before the lecture, and we've been talking about like, what is the best way of proving things? Picture, right? So, what I want to do, I want to first, define some symbols, like By this symbol, I will denote a neural network with, let's say, L layers. Think about it, something like a directed graph, right, with nodes and edges, right? L layers, or like organized into L layers, and by dimension n, I will understand the size of each layer, the size of layer L, size of layer L minus 1, etc., size of layer L naught, right? And the input layer is going to be equal to n, and that's like, at least for this notational argument, and 1 will be the dimension of the network's output. Okay, so like we have something which potentially can have many inputs, and we'll have just one output. So following the classical assignment, we also need to introduce somehow like represent a network as a map, and you see like it's a composition of affine transformations here, right? And some nonlinear function phi, sigma applied to this whole thing component-wise. There is one thing which I want to bring your attention to in this setting. By this theta of phi, theta capital of phi, I would like to denote the vector of all weights and biases, basically the vector of all parameters of that neural network, right? And also, I would like to assume that I can place those parameters in some linear vector space where there is a norm, so I can actually compare distances in parameters. Let it be, let's say, L2, appropriate L2 space. Right? And from the activation function, I would like to demand that it's not an arbitrary activation function, but it's, let's say, flat to the left of some threshold theta, and distinctly monotonically increasing to the right of the theta. So you can think of, say, your ReLU function. It will satisfy this condition. If you also think of, let's say, some versions of, say, leaky, before I said that, in principle, though, I don't have to ensure and request that this is strictly monotonic everywhere. It's just enough to be strictly monotonic on some interval from theta to some number, right? And whatever happens with the thing, like, I don't care. Right? So, but I don't want to mess the perception of the statement with these additional constraints. What I'm just like, it's crucial that, let's say, it's flat to the left of the threshold theta, and this strictly monotonically increasing to the right, and of course it's continuous. Huh? Now, data. It's important that we speak about the data, and we define the data. So I would like to assume that the data are IID samples from some distribution that belongs to a family F of distributions supported on, let's say, the cube in Rn, like with the site 2, centered at 0, by the way. And here is a product of this cube with 0 and 1, which are essentially the labels, right? Like a binary classification task. There are two classes, the classes corresponding to 0 and 1. And this is where the distributions I am interested in are going to be supported on. Now, for any given distribution D from that family, we assume that there is a training and verification algorithm which has an access to these samples, yeah, the training and testing samples and verification, right? And those things are drawn, of course, independently from this distribution D. And I would like to call the training set by capital T and the validation set by this capital letter V. And I would like to also say that these are multi-sets. So like they're not sets, they're multi-sets. So like entries can repeat in this set. So data non-degeneracy. This is an important part because since I'm talking about stability, what I want to be, of course, I'm going to cheat in the end, right? I have to, but I have to remove, like distance myself from some obvious pitfalls and obvious things where the data may potentially concentrate somewhere. I don't want this case. I want that the data does not concentrate. So, for example, what I want specifically is like for any like delta, which I pick from this interval, we will only consider distributions, the delta from this family supported on this set, right? For which the points corresponding to different classes, right? The X and Y parts of these pairs, they are at least delta away from each other, right? So I want the data points to be clearly separable. I don't want them to be arbitrarily close so that I can exploit these instabilities later, right? Okay. And yes, yes, of course.
Here we are talking about very specific case that we don't have real variables classes.
Yes. 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 So, and that's on purpose because I want to give you an example of a task which is easy, apparently easy. It will be actually very easy in the end, you will see it. But what I'm going to say, there are those tasks which are apparently easy, but then they are not so difficult to they're not so easy to verify in the end, right? So, so yes, and then as a loss function, I take any function of the following type where, let's say, the value of Re of W and V equals to 0 only when the V and W correspond exactly, right? So like the loss function is such that it's absolutely 0 when you have an exact match. It can be anything, right? Like anything positive, of course, when you don't have that match. And here comes the statement, the first slide. So it reads very complicated, but in essence, it's not. So like consider the class of neural nets, which I just specified essentially having n layers, and with an input dimension d, and the second layer larger or equal than 4. And whatever happens with other layers, I don't care. And I want that the input dimension is larger or equal than 2. So you have the activation functions, g theta, and you have the output function as an output function, you have just a threshold, right? So, and then you pick as an n, actually minimum of these two numbers. And then this minimum is pretty much defined, right? Because I want like n1 being larger or equal than 4, so like this is larger or equal to 2. So like I can, like n is larger or equal than 2, right? So, and then I pick an epsilon from that interval. And then I fix a delta. So like epsilon I pick, a delta I pick n. Right? So then there is an uncountably large family of distributions d delta, because like first of all, like you can see how the like uncountability emerges, because I can pick delta any, anyhow, like whatever I want. So such that for any training and validation data T and V drawn independently from that distribution, with probability 1, the following happens. First, there exists a perfect network that solves my problem in the best possible way, right? In terms of the accuracy. And yet, for any Q from that interval from 0 to 1/2, with probability larger than 1 minus this, where M is the cardinality of the training, right? And is it like, yeah, the cardinality of the training and validation set? There is a subset whose cardinality is at least that large, on which the network is unstable, in the sense that for any pair from that set and any alpha bigger than 0, smaller than epsilon over 2, right, which I fix over there exists a perturbation psi smaller than alpha over square root of n, so that the classifier swaps the label. And in fact, to make the matter worse, I'm going to say that not only there exists a perturbation, but you can generate it by a random draw from a uniform distribution in a ball, right? Whose size is alpha over square root of n and centered at 0. So, and if I do that process, then I'm going to hit instability with the probability of 1 minus 2 to n at a single point, right? So again, there exists an accurate network which is giving me a loss equals to 0, and yet on a sizable chunk of training and validation set, the whole thing is unstable. And it's unstable in a very peculiar way because I can reveal the instability by just randomly drawing, right, a number and adding it to that point. And with high probability, I'm going to reveal that instability. Now, moreover, the ladder perturbations are universal. Think about adversarial examples and adversarial examples with universality, right? Like we've read papers about that. Now, universal in the sense that they destabilize more than one point, in fact, with high probability. The same thing can be applied to many things. So like once I made the draw, and with this probability, it's going to destabilize some other points. Right. At the same time, for the same distribution, there is a robust network, right, which is minimizing the loss and also doesn't solve the label for reasonably sized perturbations for any of them. And here comes the most interesting part, which I want to talk about, and I would like to maybe stop a little bit here and take a pause. Remember regularization, right? Like we are told like, you have to regularize your weights. You have to make them small, right? Make them small, those weights, and then everything's going to be nice. Probably not in classification tasks, because if you give me one arbitrarily small number and one arbitrarily large number, as large as you wish, what I'm going to tell is that I'm going to give you two pairs of networks. In each pair, one will be unstable, the other one will be stable. And one pair will be lambda small apart, right? Like it will be arbitrarily close to each other in the weight space. And the other one will be arbitrarily far. So what I'm trying to say is that you cannot get away by just regularizing in that sense, which we typically would understand, like bring the weights down to nearly 0. It's not going to help you. So, and that's what I want to say. Like there are some not only bad problems, but there is a continuum of bad solutions too for the bad problems, right? So, and here comes the last part. The last part is this. However, for the above robust network, there exists an uncountably large family of distributions for which the robust network, right, classifies both training and test data, yet fails in the same way as I stated in 1. Right? So that robust network will have some tasks on which, of course, it's going to fail, right, in exactly the same pattern. So, and then there exists a large and uncountably large family of distributions, of course, that the map is robust on the training and validation set, but unfortunately unstable on the points with this probability on k other points, right, with this probability, right? So that's the paradox. And again, it sounds really fascinating, and it looks very fascinating because somehow, like, that's what we are led to believe when we read classical books. Make your loss small, regularize, and everything's going to be fine. No, So if you make a loss small, and if you regularize, there is a chance that things will not go well, right? And there are some tasks. There is a continuum. And here is what I want to say. Remember, we've been talking about the typicality. What is it? Like, what is it, typicality? And one of the criticism of the whole argument, and that's going to be a valid criticism, you're going to tell me, like, continuum, but what does it mean? Because is it big? Is it small? My answer is I've got no clue. So because like there are some mathematical works, not in this area, but in the related, like not in actually related area, in dynamical system theory. So if you think about this famous results like Smale's, let's say, nightmare, where people ask themselves, what is the size of structurally stable problems? Like people have been looking at this, like because that was very important to understand if the world around us is structurally stable, is it typically stable? And the guy showed that unfortunately, structurally stable systems are nowhere dense. So it means that there are some open sets of bad systems, right? Unstable systems. So like what I didn't put this on the slide, it's still going in an open project. Please join me in that quest if you're interested in this, because I think this is like, there is an opportunity to make a splash here, because the next step, what I want to show is, are there open sets of bad problems with the same property? Because if you can prove that there are open sets of bad problems, and we sort of done the Smale's analog of Smale's nightmare for data-driven and machine learning. Right? And do I need to reveal my workings to you? Like probably I will not. I promise that I can show you the proof. Let me show the proof. So that's the idea of the proof of the whole argument. So if you're interested in having a look at this and just think about that. So the whole thing hinges on the following property. Like again, like it's a very well-known mathematical scenario where you have, let's say, like a double description problem. Like you see, like any polyhedron you can define as through the vertices, right, or through the faces. Like in a way, it's dual. Like you can define it both ways. Sometimes definition through the faces is important and advantageous, and sometimes definition through the vertices is advantageous. But in these particular examples where I'm working with cubes in Rn, so the number of vertices is exponential, and this is where the counterexample is coming from. Like you basically place your data, the support of your distribution around those vertices, right? And we have exponentially many points at which things can go wrong. You'll have to check at all of them, and you don't know where things are. Remember the distribution agnostic setting, right? So, and yet at the same time, the solution which implements, a separation, and that's like the question of like, why do you want a separation? Like that's why a solution that implements the separation is extremely simple. You just need 2 times n hyperplanes, right? And another one to combine them all together in a single thing. So in a one sense, like you have a very simple solution solving very difficult task, but in a way you can solve it, but verification of that solution becomes difficult. Right? So that's how the argument is built. So now some reflections which I wanted to do. So is this a no free lunch type theorem? So there is a sense of it, like there is a no free lunch here, like, but it's not, because I'm not talking about behavior on average, right? I'm just saying that there are bad tasks. We don't know, like how to average them. We don't know if they're typical or they're not. And what I wanted to add here, let's say, like there is this paper published in 2023, where people said, well, people have been talking about no free lunch, etc., like, and some been criticizing this counterexamples to inductive learning. But the thing is, real life and real problems are typically good in a way that they're compressible. If you think of, like, say, Kolmogorov complexity, right? So like a good problem which we are happy to use and solve, probably it should have some compressibility in it, and therefore the space of all problems which are relevant to us, at least like we cannot learn an uncompressible problem. So they should be compressible, and that's why the argument say like probably the space of problems we have to focus on is much smaller than let's say, you know, the space of all problems. But the counterexample which I constructed in that theorem shows that the solution is simple. The problem is compressible, and it's not that which is a culprit here. It's something else. So the other thing is, right, are classification problems bad? And I just would like to recall this definition which we used. I don't know what you think about this, but I think they are inherently bad. So like we typically teach students, right? Here is your favorite MNIST problem. Here is your fashion MNIST. Here is your CFAR. Like, take them, and they are much more easier than some regression problem. But the problem is, classification problem probably is inherently flawed in the following way. You have to make a decision at some point, right? You have to decide if it's 0, 1. You cannot return both. But if you are deciding if it's 0 and 1, you are creating a discontinuity in your decision. So like, it could be that the Lipschitz constant, because that was exactly the mechanism, like in the warm-up 2, like from the Bartlett's book, that was exactly this discontinuity was a mechanism why you lose generalization. So that would be the attribute of the problems. And here is the struggle like between complexities. So classification versus verification. I sort of hinted at it already when I was presenting the whole thing. You see, one of the advantages somehow of machine learning is like of modern theories, at least as we know, was a very fundamental realization that, let's say, when we write risk bounds, right? Instead of considering all hypotheses, which are the continuum in many instances, what we do when it comes to classification, we consider the dichotomies which can be implemented by your classifier. I mean, like different splits, right? From input-output perspective, not in terms of how they're constructed. So, and that's where, you know, the leverage comes from, because now we know that if the system is limited in a way that it cannot reproduce arbitrarily long, exponentially like large dichotomies, basically that is limited in its own right, then learning happens. And that's where, say, Vapnik and Chevanek's theory and like, you know, other classical basically theory, that's how it works. Here, we have a verification problem. Verification problem is different because, like, suppose that you solved your classification problem. You found the dichotomy you are happy with. But the problem is within that specific dichotomy, by dichotomy, I understand this input-output behavior, which is fixed already, right? Like a function just like implements this splitting of things. There could be infinitely many ways in terms of parameters this can be implemented. And that's the complexity now. Like, if you want to solve it and you want to check it, you have to very carefully assess this parametric setup and also assess it against your training and test set, and also against the data which you have in the future, which you don't have. So that's another thing. And here is another one. So that's the, can you certify robustness? Some people say you can, but I hope that I gave you an example where it's going to be very difficult. And here is an example of a paper published in 2019, and it's called Certified Adversarial Robustness by Randomized Smoothing. And guess what? The paper is, of course, mathematically correct. But here is a catch. So the catch here is that, like, if you read the statement, like, let there be any measurable, deterministic, or random function, blah, 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 and epsilon being some random regenerated noise, a Gaussian noise with the variance or sigma, etc., like mean equal to 0, and then you apply it to your classifier. And what you do is that you compute this bound PA, where, like, what the measurement is that you measure what is the probability that, you know, like, after the application of the noise, a swap doesn't occur, right? Like, you have a query point X, you start perturbing the whole thing at random, and you measure the probability that the swap thing doesn't occur. And if you know this bound, then this theorem says that you can have this sort of randomized classifier, which is basically like randomized smoothing, and that's why the title. And that randomized classifier will be robust up to this margin. Now, everything is correct. The problem is, in high dimension, think about like 100-dimensional space, you cannot accurately estimate this slowdown, unfortunately. That's not going to work. So here is a catch. Yes, there is a theory apparently, but we cannot use the theory. So, and here is another one, like a bigger picture of like what and how things can go wrong. And I would like to keep adding these things because on Friday, Professor Garban will be talking about if something goes wrong, what can you do, right? So that will be the lecture on Friday, but I would like to set this scene now, saying like there will be cases when something may go wrong. Okay? So yeah, there are like cases, like let's say poor practice, and there could be biases, there could be some technical challenges, what I mean mathematically technical, and they are potentially avoidable, right? So there could be this issue, distribution agnostic setup. This is where it starts becoming foundational, and at least I hope that I delivered the message today that there are some issues in the foundations which we just cannot put under the carpet. We should be aware of those issues. And like there are things like dark data. You know, this David Hand brought a book in 2020 when he, like, in a very clear way explained what it is. But in essence, it's a data which we know exists, but we don't have access to this data yet. Right? So it's that sort of like dark data. We know that it's there, but we don't know how to get it. So and the objectives, and here is this objective. Do we really know our objective? And somehow I would like to bring this thing to us to have a look at. This is taken from the book by Stuart Russell. It's called Human Compatible. This is a very nice, popular book. And in this book, he presented a dream theorem of any machine learning expert, right? I would love to have such a theorem, but I don't think it's possible. So, right, the theorem is this. Suppose we have a machine that has components A, B, C connected to each other, blah, 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 with some internal algorithms that optimize the feedback and define so and so, blah, blah, blah. Then with very high probability, the machine's behavior will be very close. I'm happy with very close even, in value for humans to the best possible behavior realizable by any machine with the same computation and physical capabilities. Right? The problem here, and that's exactly the whole point of the book, is that unfortunately, the best possible behavior is not available even to the human themselves. We don't know. So there will be always a gap between what we expect and what we have. And that's an important point. So, right. You know this quotation, of course. So, any man can make a mistake, but only an idiot persists in errors. So we must not say every mistake is a foolish one. So here is my take on that. Unfortunately, many modern AI systems persist in errors. And it's our task as scientists and researchers to change that. And that's, again, like going to be the hope of this series of lectures. So, and finally, just before I conclude, somehow like all what I said now, and somehow like you already see where these things go, all what I said relates to a system where you design the system once, it's set in stone and it doesn't change. It doesn't interact with human, doesn't interact with expert, doesn't interact with anything, and it just set in stone and changes. So like for those systems, unfortunately, there are always going to be these sort of paradoxes and mishaps. And probably we probably need to think about systems which are not frozen. And here comes the final slide of today's talk. So I hope that I conveyed that decision making in systems, in AI systems with fixed structure, is going to suffer from some form of stability accuracy trade-off. Like I just gave you one, but it's not the only one. There are other paradoxes, I'm sure. Now, instabilities, and it's important to stress that they are in fact instabilities, they may not be cured by better algorithms. What I mean by better training algorithms is like those algorithms which try to minimize the loss. Because this counterexample which I presented, you have the zero loss, but you have no clue, right? So more data doesn't help you. Now, main causes, in fact, is the combination of the distribution agnostic paradigm. That's the strive. That's what people want. I want to get something without knowing anything. Do you think it's possible? I'm not sure. So, and at the same time, we are working living in the area where the number of data attributes is already becoming large, right? So that we cannot even hope to explore the domain. It's hopeless. So, and that's where the causes are stemming from. So, and what I claim, I hope, and you would agree that delimitation is probably foundational because it applies to artificial and natural systems. I'm going to suffer from exactly the same paradoxes in machine learning. So, and then the resolution to the paradox is probably to do something and rethink about how we design those models. So why don't we design models enabling them to adapt, to change, to start communicating with us? And probably that's the way to go. But then there will be a question of how we're going to guarantee that even this addition is going to work. Probably it's going to be a vicious cycle. Is the process going to converge under some conditions? I have no clue, but maybe that's the way. So, and like, again, yeah, it's always like this, like some grumpy mathematicians come and destroy life for everybody. So, but yes, and no at the same time, because in a way, knowing how things may fail is going to help us with developing better systems. And I think on this note, I will stop and thank you for listening to me. Thank you. Any questions? Sure.
Are you talking about the impediment that we can have an unbounded Lifshitz constant for classification problem, but maybe we can redefine classification problem in some ways that we want to output something between 0 and 1. And so in this case, would it be solvable?
Yeah, this is a brilliant question.
Thank you.
I think the answer is yes. I haven't proven this, but I think the answer is probably you can solve that. Now, and in fact, there are some approaches, for example, and I think I wanted to talk about this in my field lecture, for example, like somehow like measuring the distance to the boundary and abstaining from the decision making. Like that's pretty close to in spirit to what you're saying. Like I don't want to work at the boundary where things are bad, right? Or like even as you said, like redefine the setting, right? Like don't force that. The problem is by doing so, we are going to, I believe, suffer from something else. And what does it? So, because yeah, I was thinking about that. Like, you know, the whole beauty of dichotomies, which is the classifications, is that all of a sudden you have, let's say, a neural net which lives in some infinite dimensional space, like it's an object, but lives in that space, and you can parameterize those things as you wish. But then this going to the dichotomies enables you to tame the complexity of the expressivity, right? So all of a sudden, the complexity becomes polynomial in a way, because VC dimension like kicks in, and then like you have the polynomial. Now, if you go back to functions, we will lose that, right? We will lose this property, we lose the kind of like taming like of this complexity, and we'll have to work with something else, like let's say covering numbers, right? Like, but those will start scaling exponentially, and like depending on the resolution that you're working, you'll get more and more and more and more. So yes, you probably can solve that, but you're going to pay the price to prove things. I think that's a very, very interesting balance. It's beyond the stability accuracy, right? It's like stability, accuracy, well, data availability, computational, whatever power.
Rarely consider adversarial examples for regression, for example.
Yeah. So like it's adding an additional dimension to that, right? So yes, potentially avoidable through that route, but then going to pay back something for that gain. Yeah. Welcome. Yeah. Thank you.
Get a couple of probably naive questions.
Sure.
How to express my physicist perspective. So first of all, when you said this relation between accuracy and stability, my first association was the uncertainty principle of physics, which has also implementations in mathematics as well. You know, it is, let's say you're measuring the particles included. So if you persist, in the words of Cicero, if you persist, then this particle, after being measured with such an accuracy that you are imposing as an idiot, will immediately jump away.
Yes.
Because it will lose its, stability.
Yes.
And the question is, there are other uncertainty principles like that, not in terms of the dimensionality, but in terms of how we learn can be related to how much we can lose if we shift a little bit. The second question is, when you're talking about the density of subsets of stable points, I was wondering whether you can just cure those points by a little smearing, an ensemble, a little family of different but close networks. This would seem to be an affordable approach. Just train a family of similar networks, and then democracy.
Yeah, both questions are brilliant. Thank you very much. So like the first question about the uncertainty principle, that's a part of my current research program. I think there is an uncertainty principle, and there could be many uncertainty principles in this. Exactly. So like I think actually what we are discussing now actually calls for a program on uncertainty principles in machine learning, because understanding that will push the boundary of knowledge immensely, because like at the minute we don't have this principled machinery, right? It would be absolutely important to have that, but I'm not aware of many. So the second question about the ensemble, yes, of course. So things will work, and you can avoid this like sharp instability by doing this. Absolutely, you can avoid that. Now, however, from like, I can easily modify the statement, right? By pushing these things away from the corners and reformulate the statement that there will be some small neighborhood, like in a way, like I'll have this like epsilon stability, but this epsilon is going to be very small. And if I have a perturbation exceeding that epsilon, then like I'm done. Like the whole thing will be unstable. So like, and it will still remain the same. What's going to be even more, and that I'll talk about on Wednesday. Apparently, when the dimension is high, even just like, as we discussed, of course, small distance away from the decision boundary doesn't save you. Somehow, like what's going to happen is that you will experience some perceived robustness to big and massive perturbations. But there will be little changes in some finite directions which will take you over, right? So the question is, do we want them? Do we like neglect them? Do we assign some small measure to those events? It will be up to us. But they will, those things will persist. So like in a way, we can somehow like brush things away, polish, but underneath there will be something lurking, right? Yeah, exactly. Right. Right. Good.
Ivan, thank you very much for this very interesting talk. I like it especially because I personally have had some problems with this artificial intelligence, and one of the problems is that you cannot appeal in practice.
Yes.
Yeah. And my question essentially is the following: do you know, are there any plans to incorporate somehow the appealing procedure to these decision-making systems? Because this is one of the problems that we meet if we are rejected by the system, and the standard answer is go to hell. The black box told you are bad, and that's it.
So absolutely important point, because it relates to what we are discussing here. As far as I know, I think European Commission is pushing very hard for any algorithm to have some explanation so that the customers are protected. For example, like when I'm applying for a loan in a bank and I get rejected, I want to know on which basis I get rejected, right? So there is this program that, like, I think it's going to be a legal requirement for all the companies, for all providers of this AI decision making to explain. Now, the level of explanation, though, is again like is something which is not very clear. So, and I don't think you can actually even have it unless we regulate models of reality in this application, right? Because then it will be very difficult to explain. We know this Rashomon effect in statistics, whereby like you have a model, you have some data, but different factors equally well describe and explain the thing. Which one is which? That's the question. So, and again, like, because if we don't have a principled model, I don't think we can solve that. We can, you're right, we can in fact impose as many regulation requirements as we wish, but whether we would be able to satisfactorily answer and deliver I think it's not possible unless we define the problem properly.
So when we use this automatic translation, for instance, and
Yes.
the system gives us some wrong word, it's okay, it's not very nice, but it's not dramatic, yeah?
Yes.
But as you, in your example, or we can bring a lot
Yeah.
of other very important
Yes.
life examples. Of
Yes.
course, the clients want to know what's the reason. And
Yes.
so far, according to my understanding, it's absolutely absent. Okay, maybe it's somewhere.
Yeah, it's absent,
Absolutely.
and I think, well, there could be an explanation of the type. Look, here is the data. Like statistically speaking, these are the. I would, if I am the one who responds, I would say this is how I measure risk.
Yeah, okay.
Right. According to this measurement, the risk of this application is high. I'm going to explain why I'm measuring it that way. Fine, I can explain that, but that's my decision making. So
Yeah, I see.
yeah, it's easy
Thank
to
you
get
very much.
away, right? Yeah.
One curious.
Yes, go ahead.
Is there a way to? Just a question that came up to my mind just now. Just a curiosity. Is there a way to estimate the Hausdorff dimension of those points?
Oh, so about the dimension, there will be a talk. Like doesn't matter. Like let's not fix on very deep question deserves specific lecture, because the question is, what do we mean by dimension? What is it?
Yes, not necessarily Hausdorff one.
Exactly. And the question is, it depends, really depends on the task. There are some tasks where you can have a very specific definition of a dimension. And in fact, you will like this because it will be grounded in sort of like the world of like notions of statistical physics. So like, but then it's not necessarily like similar and identical to the ambient dimension where the thing lives in, right? It doesn't have to be, right?
That's why I asked this
Right.
question.
So, and we have just like, it's good that you are like, did you see what I was working on? So like it's just today when we, I had a conversation with some people from my group, and they said, look, Ivan, we finally cracked it. In a way, formulated some theorems about success of solving problems exactly in terms of dimension of the data. Don't ask me how and what this dimension is, but this is very, very important thing, because I don't think there is one single definition of dimension. I think it's also relevant.
Spectral dimensions.
Exactly,
for example,
relative to the
many-
task, relative to the task you're solving. So like, I don't think there is a general thing. Yeah, and sometimes you can estimate it, and sometimes you can write a theorem or statement, but then when it comes to like measuring it physically, you are in for a good ride. It's like it's probably not always possible to estimate it properly. So
Yeah, sure. It would be interesting, for example, well, that's just my take on that. It would be interesting to estimate this dimension for a given set of
Yes.
samples, for example.
yes,
Say for breast cancer
yes.
in the US, if you will.
Ah, that's interesting, because Alexander Vladimirovich knows everything about dimension in this sense, like and the geometric interpretation of data. Yes, like there are some models that enable you to do that. At least like when you use the concept of data manifold, we can think about dimension locally, right? But I think it's a different lecture now. Yeah, thank you. But
Thanks a million.
Yeah, thank you.